So this is really a multiple group of sections that we're going to talk about, but it's 10.5 through 10.7. And we have all of it I'm calling the shifting theorems. And what's called the Heaviside function. Now, by the way, some people call shifting theorems, they call them different things. So that's something you sort of have to get used to, is with sometimes different textbooks or different crowds will call these theorems different things, but our book refers to them as the shifting theorems. And then the Heaviside also gets another name as well that we'll talk about, but I refer to it as the Heaviside. So first of all is the first shifting theorem. And what the first shifting theorem says is if I have a Laplace transform of f, and that's equal to this transform of f evaluated at s, so lowercase of t goes to big F of s, then if I take the Laplace transform of e to the at times f of t, so now I've got a product of two functions, e to the a with the input t and then multiplied by a function of t, then that is equal to capital F evaluated s minus a. And it's important to remember here that the a are the same. So the e to the a t and then equals f of s minus whatever that a is. And it gets called the shifting theorem because we are shifting the function to the left or to the right depending on the value of a. And the converse of that is also true if we are taking the inverse Laplace transform of capital F of s, and that's equal to f of t, then, so this is the inverse of what the first shifting theorem says, going the other direction, then capital F of s minus a, its inverse is equal to e to the at times f of t. And this is, both of these are very, very powerful tools. Often they show up on your Laplace transform tables like this, where e to the at multiplied by a function f of t equals, and then it'll show that it transforms to capital F of s and a. And on your table that you have, it doesn't explicitly say that, but some tables it will show up as its own sort of line on the table. And then sometimes it's just that you're meant to know what the first shifting theorem is so that you know how to do that on your own. So let's do an example. So if I have a function f of t equals e to the 5t times cosine of t, so I look at my Laplace table. In my Laplace table, I find what f of t is, or the, not f of t, but what this part is, which is this part. That's why I said I look at what the f of t is. So I look at the Laplace transform of cosine of t, and I'm going to write for emphasis 1 times t. And when I look at my table, I get s divided by s squared plus, and then it would be k, but here it's just 1 because it's a 1 times t. And on your table, that would be number 7. So cosine of k times t, or cosine of a times t, is equal, when I take the transform, to s divided by s squared plus a squared, and that's number 7 on your table. So in this case, that a, or k, is equal to 1, so we put 1 squared. So that's that part of the transform. That's what I find first. And then what I do is take this first shifting theorem, so the Laplace transform of f of t would be the Laplace transform of e to the 5t times the cosine of t, and then that would be equal to s minus the shift, which would be 5 in this case, because that's what this is, that's 5. My 5 kind of look like an S, so let me fix that to make it look like a 5. E to the 5t times cosine of t, so it's S minus the shift, which is 5, and then divided by S minus 5 quantity squared plus 1. And that would be the transformation. And it's important to see that this is where the S was, so I do minus the A. In this case, the A is 5. And then this was S squared, so it's S minus the A at quantity squared. And so the first shifting theorem allows us to take reasonably complicated functions of t and transform them easily into this Laplacian space. Let's do another example. So how about f of s equals 6 divided by s minus 4 cubed. So now we're in Laplace space, and we want to go into this t space. So if I have 6 divided by s minus 4 and I cube it, that's equal to 3 times 2 on the top, and then s minus 4 times, or raised to the 2 plus 1. That would be the same. And I made a little note to myself here. If on the table I look at n equals 2, then I have 3 times, so that's this 3 I pulled out front, times, and then 2 factorial divided by s minus 4 raised to the 2 plus 1. That would be the same. And then I made a little note here that my a equals 4. And so if I take the Laplace transform, and its inverse, so the inverse Laplace transform of 2 factorial divided by s to the 2 plus 1, so that would just be unshifted, I get 3t squared. So that's just the reverse transform, and that's number, on your chart, that's number 2 on your chart that you have. That's number 2. And then, of course, being multiplied by this 3 that's out front, so that's why this 3 is there. But we also have this this minus 4 business, this a, to deal with. And so that's where our inverse of the shifting theorem comes into play. So I take the inverse Laplace transform of f of s, which is the inverse Laplace transform of this whole thing that I'm going to write 3 times 2 factorial divided by s minus 4 raised to the 2 plus 1. I'm going to write it that way, emphasis, and then that's equal to this 3t squared. And that comes from here. And then I also have the multiplied by e to the at, which is 4t. Now, I've written that in a different order than what we wrote up above. We wrote it in the other order. We wrote the e to the at out front and then multiplied by the f of t. But it's the same. I've just written the e to the at on the other side. So if I wrote it in the way that we wrote it in the theorem, I'd have e to the 4t times 3t squared. And so this is the shifting theorem that I can go back and forth and save myself quite a bit of algebra and a headache when I'm trying to figure out how to make these transforms from t to the Laplace transform space and then back. So this first shifting theorem is very powerful to help us with that. Okay, so now let's talk about 10.6. So this is, I'm going to title this the forcing term. Our book refers to it that way from time to time. And I've not seen, there are other textbooks who do that too. They'll call things this forcing term, but sometimes it gets called the function term. So it's the forcing term. Sorry, I had a glitch on my end over here. I think I've got it fixed. Forcing term. And many applications for example, we'd have y double prime plus by prime plus cy. So first derivative of y plus b times the second derivative of y plus b times the first derivative of y plus c times y equals f of t, with f of t being a piecewise continuous or discontinuous. And these are hard to solve without using a Laplace transform. I'm not saying you can't solve them, but they are difficult to solve. They're often difficult to solve even with a Laplace transform, to be honest. But we'll do our best with the Laplace transform. And so this term forcing term comes from the f of t. I should use lowercase f. This f of t is often called the forcing term. Okay, so that brings us to this very important definition, which is called the Heaviside step function. And sometimes it gets called the unit step function. And what it looks like is u, the notation that usually gets used is u sub a of t, which is equal to, sometimes it's written as u of t minus a, is equal to the piecewise function 0 if t lies in between 0, including 0 and a, not including a, and then 1 if t is bigger than or equal to a. And so this is the Heaviside definition of a Heaviside function. And the way I view it is as a switch turning on and off. So I have this sort of, I guess, electrical engineering view, you would say, about a switch turning on and off. So in terms of a switch, so like I have an on and off, or maybe you would say like energized and de-energized, or engaged or unengaged, or signaling and quiet, right? There's a lot of other ways to say it, but I say on and off. So our goal then is going to say, well, we want to turn on our function and have it on, and that when we do that, we're going to multiply it by 1, and then we're going to have off, which is we'll multiply it by 0, is sort of my point of view. One thing I want to mention with some notation here is I view the u sub 0 of t to equal 1. So the u sub 0 of t to equal 1. And if you look at the reason I'm going to call it that is because u sub 0 of t as a piecewise function, this would be 0, and 0 less than or equal to t less than 0. Because remember, the a, which is here, goes in these spots. So this is 0, so that's going to be a 0. And then I have a 1, and that's t bigger than or equal to 0. So if you're talking about u of 0, then you're talking about the situation where t is bigger than or equal to 0, so that is 1. So that's the first thing I want to mention, is that I call this u of 0, or a u sub 0 of t, I call that 1. And then the next thing is this u of a of t. So u sub a of t, we're going to call this on at t bigger than or equal to a. And so this would be the on function. I'm going to call that the on function. So if I drew a picture, I would have u of a of t, and then this is 0, and this is some spot a, and 1 up here, and my function would be off from 0 till I get to that spot a, and then it gets engaged at a, and it's on. So this is on. And this is happening, this change is happening instantaneously. And sometimes that instantaneously is a false statement in terms of the fact that it's not actually instantaneously. It's just happening so fast that we can't actually measure it. So when I energize a circuit, the time it takes for that circuit to energize is unmeasurable. It's so small. We don't have that capability at this point in time. Or the time it takes a certain explosion to take place, or chemical reaction to take place, is so, the time it is taking is so epsilon small that we just can't measure it. So we talk about that being instantaneous. And so we jump from off to on in this instantaneous way. So this is the on function. So I'm going to draw a square right around that. Then the next important piece to our puzzle is if I have f of t, so I have this function in terms of time, is equal to u of a of t, so u sub a of t, minus u sub b of t, where b is bigger than a, then I call this the on/off function. And this looks like this f of t as a piecewise function would look like this: 0, 1, and 0. And for the initial 0, I would have 0, t is in between 0 and a. And then it is engaged when t is in between a and b. And it is off again when b is bigger or equal to t. So this would be your on-off situation. And if I drew a picture of that, it would look like this. Then would be f of t. This is 1, and this is an a. That looks a little open there. Let me fix that. This is a, and this is b. And then what's happening is the function is off from 0 to a. We switch it on, and it becomes engaged at a, and it's on until it gets to b, and then it's engaged at b. So this is an open circle up here. It's engaged at b and runs on. And so this is our on-off function. So we've switched things to on and off. Okay, so those are the three situations. Now, for this on-off function, I've made this claim, and I've said that that's true. That's how you should think about it. I encourage you to do a little algebra, or at least make yourself a table to convince yourself that this ua of t minus ub of t is indeed the situation. And I would suggest do something like this even. Make yourself a table, f of t, and then put your t values over here and your f of t values over there. So make yourself a table with t and f of t, and what's happening at 0, and then figure out what's happening at f of t, and then what's happening at a, what's happening at b, and what's happening at b plus 1, so like the next thing. And so look at those two definitions with the u of a and the u of b, and work that out on your own. See if you can convince yourself of that. The other thing you could do would be to graph those things. So in something like Desmos or in anything else, that you could do a piecewise function, define a u of u1 of t, and then you can't just use an a, but use a u1 of t, and define a u2 of t, and then type in the u1 of t minus the u2 of t and look at the graph that decimals produces. But I encourage you to sort of argue that out in your own brain and become comfortable with why that would be the case. But that's really algebra from a class before, but we maybe have never have applied it that way. All right, let's look at an example of this situation in practice. So this is from number 8 from section 10.6 from our homework. So I've got a function f of t is equal to, and it's a piecewise function with 3 and minus 1, and I've got 0, t, and 1. So t lies in between 0 and 1, including 0, but not including 1. And then I've got t is negative 1 when t, or the output is negative 1 when t is bigger than 1. And then we're asked to do that on 0 to infinity. So the first thing I want to do, if I can, in these cases, is to draw some sort of picture. Sometimes that helps some people it doesn't. And I label my f of t, and I label my t, and I put the places where things are going to change, which in this case is at 1. And then, let's see, from 0 to 1, the output's going to be 3. So this is 3, and from 0 to 1, the output is 3. And then from that point on, I'm down here at negative 1. And when t is bigger than 1 and equal to 1, I have this negative 1 output. So that's what my picture looks like. And then now I want to convert that into this unit step function, or this Heaviside notation. So I'm going to think of this as it's on from t is between 0 and 1. So it's on between 0 and 1, and then off, right? So this on-off situation. And then it turns on again with t being bigger than or equal to 1. So that's what's happening. I turn the switch on at 0, and I turn it off. So maybe on, off like this, all right. And then I turn it on again and leave it on when t is equal to 1. So I'm going to call f sub 1 of t is equal to, so I'm going to do the on-off part. So this is the u of a, u sub a of t minus u sub b of t. But in this case, it's u sub 0 of t minus u sub 1 of t. So that's my on-off situation. And then I'm going to multiply that by 3. So remember, the Heaviside function is with a 1, but then I'm going to really multiply that 1 by this 3. I need to make it a magnitude of 3. And then my f2, the next part over here, let me draw it this way. So this is f sub 1 of t. It's this one. And this one will be f sub 2 of t. Will be this one. So my f sub 2 of t is equal to, I'm turning it on at 1. So u sub 1 of t, and I need to multiply that by minus 1. So that's turning it on, switching it off, being multiplied by 3 from up above. And then I'm going to turn it on, so to speak, at t equals 1, and it's going to switch to the minus 1 there. Okay, so then I just add those two together. So then my f of t is equal f sub 1 of t plus f sub 2 of t. And let's see, 3 times u sub 0 of t minus u sub 1 of t plus, and then I've got this minus 1 times u sub 1 of t. So all I've done is add them together and then written the constants out front instead of on the right-hand side. Well, then that can simplify to 3 times, and remember I said when we started, when I have this u sub 0 of t, we can always write that as a 1. So 1 minus u sub 1 of t. So I'll just recopy this, but change this to 1, and then minus u1 of t. And then I've just, of course, just simplified that. Now, I could just leave it this way, but we tend to try to simplify them as much as possible. So that way, well, you'll see why in a little while why it's important to simplify these as much as possible. So 3 minus 3u1 of t, just distributing the 3, minus u1 of t. And then I can combine like terms now, and I have 3 minus 4u1 of t. So I've converted this, this piecewise function into this unit Heaviside notation, this Heaviside step function notation. All right, let's do another example. This is example number 12 from 10.6 in your book. So f of t equals, and we have t, 6 minus t, and 0 in our pieces. And t is on from 0, including 0 to 3. And then 6 minus t is on from 3, including 3 to 6. And then we have 0 from values bigger than 6. So again, what I'm going to do is sort of think about this as I'm on and then off, switching on and off for 0 to 3. Then I'm switching on and off for 3 to 6. Then I'm switching off in this case because I'm going to be multiplying by 0 for t bigger and equal to 6. And the reason I'm saying off is because nothing happening there, right? We're going to multiply by 0. Okay, so then now I'm going to write that my f1 of t, f sub 1 of t is equal to, so I have from 0 to 3, so on at u sub 0 of t minus u sub 3 of t, and then I need to multiply that by t, because that turns it on, being multiplied by 1 from the Heaviside function. But we want to multiply that 1 times the t, so I multiply this by t. And then my f sub 2 is for 3 to 6. So u sub 3 of t minus u sub 6 of t. And I need to multiply that by 6 minus t. 6 minus t, multiplying that by. And then my last part would be multiplying by f of 3 of t, f3 of t would just be equal to 0. Right? So I would be engaging that u sub 6 of t. That's when I'd be turning on the off switch. So we don't tend to write this one. It's not wrong, it's just we don't even tend to, that's just 0, right? 0 times anything is 0. So we just sort of leave that out, don't bother with that. So f of t is equal to f1 of t plus f2 of t. And then this is equal to, I have to be careful to write everything without making any mistakes. So this is 1 minus u sub 3 of t, that whole thing being multiplied by t. And I've gone ahead and changed this u sub 0 to 1. I've already done that in the first step when I'm recopying. Plus u sub 3 of t minus u sub 6 of t. I'm going to multiply that by 6 minus t. So then I'm going to distribute this t in the first term to everything. So I'm going to have t minus t times u sub 3 of t. So, and then the second term, I'm going to distribute the 6 minus t to everything. So this would be 6 times u sub 3 of t, and then minus 6 times u sub 6 of t, and then minus t times u sub 3 of t, and then plus t times u sub 6 of t. So I'm going to go back through and check my algebra to make sure that's correct. So I distributed that t to both terms. That looks right. Then I distributed the 6 to the first two terms. And that looks right. And then I distributed this minus t to both terms. So that's minus t times u sub 3 of t, and minus 6 times minus 6 is positive t times that. Okay, so then we should put some things together that are like terms. So how about t minus 2t u sub 3 of t, and then plus t times u sub 6 of t, and then plus 6 times the quantity, u sub 3 of t minus u sub 6 of t. So I just collected like terms and put things that were in common together. Sort of, there's obviously more than one way to combine those terms. I looked in the back of, in the solutions manual to double check my work, and they've actually done one more step that I didn't think of right away, but they pulled out a t in each of these terms. So they have t times 1 minus 2u sub 3 of t plus u sub 6 of t. So just pulling out a t out of each of those terms, and then plus 6 times, and exactly what we had over here. So how far do you need to simplify? Well, the answer is I don't know. You need to simplify as far as you need to go to use this technique to solve the problems, which we'll get to very soon. Okay, so I'm going to take just a break here and find out, is anyone have any questions so far about the first shifting theorem or about the Heaviside function? How are we doing? So far, so good? All right, let's keep going along then. Okay, so now we're going to talk about chapter 10.7, and this is where we'll actually solve some differential equations. This is the second shifting theorem. So if we have a Laplace transform of f of t, and that's equal to, make my brackets a little neater, and that's equal to this f of s space, then the Laplace transform of your u sub a of t times f of t minus a. So this is our Heaviside function multiplied by a f that's been shifted by the same value of a, then that's equal to e to the minus as times capital F of s. So take note, this a and this a have to be the same. And so often when we are doing our simplification, we're working towards that goal to have a function f of t minus a lining up with our u sub a. And so how much simplification we need to do is often dictated by getting things into that form. And then, and the inverse of that is also true. If I take e to the minus as times f of s, that's equal to u of a of t times f of t minus a. And there's a corollary that follows with this. We'll also write down the Laplace transform of u of a of t times just f of t. So no a, no minus a. Well, that is equal to e to the minus as multiplied by the Laplace transform of f of t minus t plus a. Okay, so these are the three heavy hitters for the second shifting theorem. Is I can transform this Heaviside function times f of a t minus a. I can transform that to e to the minus as times f of s. And the inverse of that is true as well. And then as a corollary to that, I can do the u of a of t times f of t, and with no minus a in my Laplace transform, and that's equal to e to the as times the Laplace transform of f of t plus a. Okay, let's do an example. So, examples here. Find the Laplace transform of f of t make my bracket nicer, of f of t if my f of t is a piecewise function, 0, t minus 1, and 1, and 0 runs between, or 0 is on from 0 to 1, so t runs between 0 to 1, and t from 1 to 2, t minus 1 from 1 to 2, and then 1 is t bigger than or equal to 2. So if I say that all correctly, I have 0 when t is between 0 and 1. I have t minus 1 when t is between 1 and 2. And I have 1 when t is bigger or equal to 2. So let's see here. If I wrote this out, I would say we're on and then off, switching on and off from t between 1 and 2. We're off from 0 to 1, so I'm not going to bother with that. And then also, we are on permanently when t is bigger or equal to 2. So my f sub 1 of t is equal to u1 minus u sub 2. I should put the t's in each of these. So u sub 1 of t minus u sub 2 of t. So that's my u1 is minus u2. That's on and off again, and that needs to be multiplied by t minus 1. And then my f2 of t is just equal to u2 of t. So we're turning u2 of t on, and that's just being multiplied by 1. So my f of t is the addition of both of those. So f1 plus f2. And so let's see if we can simplify that. So this would be t minus 1. And that's being multiplied by u1 of t minus u2 of t. And then plus u2 of t. So that becomes, I multiplied this t minus 1 as a t minus 1 to both terms. That's the way I wrote it this time. So t minus 1 times u sub 1 of t minus t minus 1 times u sub 2 of t. So I just distributed the whole t minus 1 instead of foiling. And then plus u sub 2 of t. Now you asked me, say, Mr. Hadley, why did you do that instead of foiling? Well, remember the second shifting theorem, I want things to look like this, right? I want this to be 1, sub 1. Oop. Hang on just a second here. I think I lost the screen there for a second. I want things to look like where I have the 1 and the 1, right? That's what the shifting theorem wants me to do. So that's why I'm doing that, is I saw if I multiplied this t minus 1 times that first term instead of FOILing, then I would be in better shape. Okay, so let me delete these little arrows I drew here. Oh, hang on just a second. Let me share my screen again. See if I can get this to work better. I think it's working now. So I've multiplied that t minus 1 to both of those terms. And let's see, what else can I do? Well, I'm going to leave the first one alone for the reasons that I said. I have this nice t minus 1 situation with a u sub 1. So I'm going to take advantage of that with the second shifting theorem. And then if I rewrite this where I pull out a u sub 2 times t, I would have, so I pulled that out of the third term and the fourth term, and then I would have a minus t plus 1, and then plus 1 left over. And sure enough, that's going to be awesome, because then I'll have a t minus 1 times a u1 of t plus u2 t, and I'll have a minus t plus 2. So I just factored out the u2 out of the third and fourth term, and it left me with a minus times the quantity t minus 1, which I made minus 1, which I made minus t plus 1, and then plus 1 from the fourth term. So then I end up with that negative t plus 2. And of course, that's not what I want it to look like. What I want it to look like is with a minus. So I can fix that by factoring out a minus, and I have minus, and then t minus 2 times u2 of t. So I've worked hard to do that because, again, I want my minus a to match up with the u sub a coefficient, and then I can apply the second shifting theorem, because that's what that looks like, right? The a matches up with the minus a coefficient. I can apply that second shifting theorem. If I wrote this out formally, I would say let's say g, we can choose any function we want, let g of t equal t. Then I would have g of t minus 1 equals t minus 1. So I put in t minus 1 there. So if I put t minus 1 there, I put t minus 1 where I see t, and I get this. And the reason I've done that is then I will substitute this g of t minus 1 for the t minus 1. And then also I get g of t minus 2 equals t minus 2. So I wrote it that way. So then I can substitute g of t minus 1 times u sub 1 of t minus g of t minus 2 times u sub 2 of t. And this is my f of t, I suppose, from way up above. That's my f of t. So then if I take the Laplace transform of f of t, I get e to the minus as, and my first term a is 1, so e to the minus 1 times f times, and then I'm going to write this as the Laplace transform of g. So I'm going to do that in the next step. And then minus e to the minus 2s times the Laplace transform of g. So I'm sort of doing it that way for emphasis. And remember, g is this t minus 1 and t minus 2, but I made those substitutions, so it's really g. And so I have used the second shifting theorem to do this part. And now I just need to do the second part with this capital F. But that's easy enough because I just look at my chart and the Laplace transform of g of t would equal the Laplace transform of t, because that's what it was equal to, right? G of t was equal to t. And the Laplace transform of t is 1 over s squared. And that's number, on the chart you have, that's number 2. So it'd be t to the first. So t to the first would be n equal to n factorial over s to the n plus 1, so 1 over s squared. So then I just put that all together. So I have the Laplace transform of f of t is equal to, I factored out both of the Laplace's transforms of this g, which is 1 over s squared, so 1 over s squared times e to the minus s minus e to the minus 2s. And that's my final answer. So that would be the Laplace transform of that problem. Now I know this is a lot. That's a lot of work. It takes a lot of practice to get it sort of fluent and right. Let me take a second here and let's see if I had any other questions. JP asked about factoring out constants for the Laplace transform. So yes, anytime you have a constant, you can factor that outside of the Laplace transform because it's linear. And so if you need to do that, sometimes you do take advantage of that situation, and then you do all the work you're doing, and then when you're finished, you're multiplying by whatever that constant was. Any other questions? Okay, let's actually solve a differential equation using this mess. It's not a mess, but all this hard work we've been doing.
Do you have another question? So for t minus 1 and t minus 2 and setting g of t equal to t,
yep,
we were just able to neglect the minus 1 and the minus 2 basically and make those forms of g. Is that what you did?
Yeah, let me pull up that part of the share again. So you're talking about right here?
Yeah.
So the reason I chose to do a substitution in the first place is because my shifting theorem tells me that if I have a u of a sub at multiplied by a function of t minus, and then those a's are the same. So this minus is what I'm looking for, right?
Oh, okay, I see, yeah.
And so I just said, well, let g equal t, since it's a linear thing, right? And then I substituted t minus 1 into this, and that's the same, right?
Yeah.
Now, it gets trickier if it's not a nice, like first order polynomial, right?
Right.
You know, this is a nice, I said linear, but I mean, you know, this is a nice affine linear, makes a line on a graph, right? And so
Yeah.
substituting for t is easy to do. It can be trickier
Yep.
than something else, like a sine or a cosine or exponential.
Okay.
You can fumble around for a while trying to figure out how do I get the shifting terms to match up nicely.
Right.
But I've picked examples and problems out of our book that are manageable.
Yeah.
They can become very unmanageable very quickly.
Okay. No, that makes sense. Thank you.
Mm-hmm. Okay, so let's solve an initial value problem here. So this was example from number 28 from our 10.7. And the directions tell us to solve the initial value problem. And we have the first derivative of y plus 2 times y is equal to 2 times the Heaviside on, like that. So 2 times u sub 1 of t. And we're also told that y of 0 equals 1. So I'm going to do sort of write it weird, but I think this helps to sort of keep track of what it is we're trying to do. So the right-hand side of the equation, I'm going to take the Laplace transform of that. And that's 2 times u sub 1 of t. And then I'm going to pull the constant out, like this. And then this is then equal to 2. This is equal to 2 times. And then this is where we have to be a little bit sort of careful that we remember what the theorems are. So u sub 1 gets us the e to the minus 1 times s. And I'm getting that. That's the easy part. That comes right from this 1, right? So that's the second shifting theorem. Gets me to that minus s. And that it's not written here, but it's implied that my f of t is equal to 1. My f of t is equal to 1. And so I need to multiply this by 1 over s, because the Laplace transform of 1 is 1 over s. And that is number 1, I think, on your table. Yep, number 1 in your table is 1 over s. So we have to be careful that you don't miss that part, because this is really being multiplied by a 1 here. So times 1, right? So the function of t equals 1. So don't forget that part. And then if I simplify this, I'd have 2 times e to the minus s all divided by s. So that's my right-hand side. And then my left-hand side is what we had from before. So I take the Laplace transform. This is from last week. Y first derivative plus 2y. And I write this as just the first part. Just this one would be capital S times capital Y of S. And then so S to the first, and then times always the big Y, and then minus S to the 0, which is just 1 I'm not going to write, and then Y of 0. And then I'm going to add this part, the Laplace transform of that. So that's going to be 2 times s to the 0th, which is just 1 times y times capital Y of s. So that's those Laplace transforms that we did from last week. And then this can be made to be s times y of s minus 1 plus 2 times y of s. And that minus 1 comes from the substitution that y of 0 equals 1. Then if I rewrite this, I can rewrite it as y of s times s plus 2. So just factoring out the y's of s in common terms. And that leaves me with s plus 2 and then minus 1. So I did that sort of in 2 steps, the right-hand side and the left-hand side. So then if I put those together where the right-hand side equals the left-hand side, I'm going to have y of s times s plus 2 minus 1 is equal to 2 times e to the minus s divided by s. And then I'm going to add 1 to both sides. So I have y of s times s plus 2 equals 2 times e to the minus s divided by s plus 1. Then I divide both sides by s plus 2. So y of s equals 2e to the minus s over s times s plus 2 plus 1 over s plus 2. Yikes. So the second term there is not that big of a deal. I think that's right on our chart. But figuring out what to do with this first term is a little bit more of a challenge, and I think we'll have to use partial fraction decomposition for that. So let's see here. If I made 2 over s times s plus 2, that's equal to some a over s plus some b over s plus 2. And so I'd have 2 equal to a times s plus 2 plus b times s. And if s equals 0, I'd end up with 2 equals a times 2. So that means a equals 1. And if s equaled minus 2, I'd end up with 2 equals minus 2 times b. So a means b equals minus 1. So I decomposed this part of the first term, and then we'll just multiply that result by the e to the minus s. Hang on just 1 second. Let me get my screen back. I think what happens is my iPad from time to time, because it doesn't sense that I've done anything to it, I guess. It like times it out. So it shuts it off and I have to turn it back on. All right, so what we'll do then is rewrite this now as, let's see, y of s, so we're doing this in black, y of s equals e to the minus s times, and then the decomposed this decomposition that we did here, which we found to be A was 1, so 1 over S. B was minus 1, so minus 1 over S plus 2. And then plus 1 over S plus 2. This got decomposed, still multiplied by the e to the minus S, and then still added that term over there. Okay, now let's see. This is equal to e to the minus S over S minus e to the minus S over S plus 2 plus 1 over S plus 2. So I just distributed the e to the minus S. Okay, so now if I take the, I'm going to rewrite it here, I think, so it's easier to see instead of going back up. If I take the inverse Laplace transform of e to the minus as of f of s, capital, that needs to be a capital letter. This is the second shifting theorem, the inverse. That's equal to u sub a of t times f of t minus a. So this is that second shifting theorem. But the inverse of it, going back the other way. And then let's see if we can apply that to what we've just found. So the inverse Laplace transform of y of s equals, and then we'll have a lowercase u of t. So that's this part, lowercase y of t. And then we have equal to u sub 1 of t times 1. And then we'd have minus u sub 1 of t times e to the minus 2 times t minus 1. And then the last one's easy. That's just reading from the chart. That would be e to the minus 2t. Okay, let me explain where all those came from. So on your chart, number 3, so 3 from your chart has e to the at, and then that transforms to 1 over s minus a. And so in our case, oh, and then also number 1 on your chart has 1 transforms to 1 over s. And when I look at up above here, this part is equal to e to the minus s times 1 over s, and then minus e to the minus s times 1 over s plus 2, and then no shifting theorem needed for the last term. That's just a standard Laplace transform, 1 over s plus 2. And so what I did was say, for the first one first, this e to the minus s from the second shifting theorem is this, where e to the minus s, where e, the a is equal to the a is equal to 1. So that's why I put this a is equal to 1. So I put the 1 there. And then 1 over s is equal to 1. A function of 1 over s is equal to 1. Now, what we need to do is replace our t's with t minus a's. That's what the shifting theorem was telling us we need to do. We're replacing our t's with t minus a. That's where this is, right? But in the case of 1 over s, there's no t, right? There's no t there, right? So there's no place to put a t. So when I replace the t with t minus a here, well, there's no t, so it's just 1. Now with the second term, this term, that's a different story. So here, minus is minus. And then I have this 1. So minus 1 times s. So a is equal to 1. So that's why I put that there. A is equal to 1. And then I have s minus a corresponds to e to the at. So in this case, I have e to the a, which is s plus 2, e to the a, which is e to the s plus 2. So this is 1 over s minus minus 2. And so I need to have e to the minus 2 times t would be the normal Laplace transform for that term, the 1 over s plus 2. But remember, I have to replace t with t minus a. So then I'm doing e to the minus t times t minus a, which a is equal to 1 in this case. So that's where I'm getting that minus 2 times t to the minus 1 because of that second shifting theorem. And then the last term is just, there's no shifting there, right? It's just a 1 plus 1 over s plus 2, which is e to the minus 2t. So I have to do the substitution when I'm using the shifting theorem. And the first part of it I know because of what is here, the a, right? This is the a. This is the a. Now they happen to be the same in this example. So then I put the a. And I put the a. And then the function, which is this part, came from the 1 over s transforms into 1. And there's no substitution, right? There's no t minus a in this case because there's no place to put that. But for the second one, this transforms into 1 over s minus minus 2. So this would be e to the minus 2 times t. That would be that case. But because I need to replace t with t minus 1, I'm shifting, then I end up getting that term with the e to the minus 2 times t minus 1. So my final answer would be y of t equals u1 of t times 1, but I don't write that, minus u1 of t times e to the minus 2 times t minus 1 plus e to the minus 2t. Now, probably we would factor out this u1 of t times 1 minus e to the minus 2 of t minus 1. We'd probably do that. So this is the solution to that differential equation. Now, folks, I warn you all that, this sort of doing that and practicing that comes with a lot of homework practice, right? You can't just sit down and expect to be able to manipulate all these things without a lot of practice. So practice those that I assigned you to do. And then let's do one more example that's like your homework. Start with a new board here. So this is number 42 from 10.7. And it gives us the same directions to solve the initial value problem. In this case, it's y prime plus y equals f of t. Sorry, I thought I had done a different example. All right, we'll wing it. And then y of 0 equals 2. And then f of t equals, and they drew a picture for us. So this is 1, this is 1, this is 2, this is 3. And then we have a straight line that looks like that. So this is a differential equation, and where we have the restricting part over there on the right side as a f of t as a picture. So we got to figure out what in the world's going on with that. Okay, so let's first draw a piecewise function from our picture. So it looks like from 0 to 1, we have nothing going on. So 0, when time is between 1 and 0. And then we have the slope of the line equals 1. And the intercept would be -1, so t minus 1. And that's going on from 2 back to 1. So that's going on from 1 to 2. So that's this part. And then at 2, it's going down, so the slope would be minus t. And the intercept would be 1, 2, 3, so plus 3. And this would be t from 2 to 3. And then, so that's this part. And then it's off again. So 0 for t bigger than or equal to 3. So this is our piecewise function on the right-hand side. And this forcing term, as our book likes to call it. All right. So let's see here. First of all, we're going to find an F1 and an F2 because we really only have on and off on those terms. So we're on off when we're between 1 and 2, and then we're on and off again from 2 to 3. So my F1 of t is going to be t minus 1 from u1 of t minus u2 of t. That's going to be my F1. And then F2 will be F2 of t will be 3 minus t. So I just switched those around from minus t plus 3 to 3 minus t. And then that's going to be from u sub 2 of t to u sub 3 of t. And then my f of t will be adding those two together. So f1 of t plus f2 of t. Okay. So let's see here. If I distribute, actually, let's just write them out first. So t times 1 of u1 of t minus u2 of t plus 3 minus t times u2 of t minus u3 of t, like that. And that's equal to, so t minus 1 times u1 of t minus t minus 1 times u2 of t. So I'm just distributing that t minus 1 to both terms. And then I'll do the same thing with the 3 minus t. So plus 3 minus t times u2 of t minus 3 minus t times u3 of t. So I just distributed each of those. This one like that, and this one like that. And that looks terribly messy up here now. Let me see if I can fix some of this to make this look nicer up here. Plus 3 minus t there. That looks a little neater. Okay, so then I just distributed to get to the next line. Let's see now. Let's put the U1 stuff together and the U2 stuff together and the U3 stuff together. And I'm sort of thinking ahead now. So you see how I have the shift with the A? U1, A is equal to 1, and then I have the T minus 1. And then I'm looking up here and I see I have the 3, U3, A is equal to 3. And this is not quite right, but I have this negative sign to fix it. So like 2 of them are already done for us with a slight modification. So I'm really hoping that when I put all of these things together, I'm going to have a T minus 2 with this 2. And again, I suspect because of the problems are carefully chosen for us, that's what's going to be the case. This one's already done. We'll see. Okay, so let's keep going here. So let me recopy. T minus 1 times u1 of t. And then I'm going to factor out everything with a u2. So let's see here. If I did plus u2 of t times, I'd be left with a minus times t minus 1 plus a 3 minus t. And then I'm going to distribute that negative on the right-hand side. So I'll have a plus t minus 3 times u3 of t. So then this is t minus 1 times u1 of t plus, and let's see here, I'd have minus t plus 1, and then plus 1 and 3 with another minus t. I'd end up with 2t minus 2t plus 4. So this would be ut of 2, or u2 of t times minus 2t plus 4, and then times u sub 2 of t. Oh, I already wrote that part. And then plus t minus 3 times u sub 3 of t. And so I don't quite have the t minus 2 that I want, but I can get there by factoring out a minus 2. So I have t minus 1 times u sub 1 of t. And then if I factored out a minus 2, I'd end up with a t minus 2. And then u sub 2 of t plus a t minus 3 times a u sub 3 of t. And that was my goal, right? Because I want to use the second shifting theorem. And I have the u sub a with the minus a, and the u sub a with the minus a, and the u sub a with the minus a. So once I have that set up, I'm in good shape. So I'm going to write this out more formally now for the substitution. Again, if I use this g of t equals t, and I did g of t minus 1, so where I see t, I'm going to put t minus 1. I'll have t minus 1. And g of t minus 2 would be t minus 2. And g of t minus 3 would be t minus 3. So then I can substitute on all of those places. So my f of t equals now g of t minus 1 times u1 of t minus 2 times g of t minus 2 times u sub t of t plus, and then g of t minus 3 times u sub 3 of t. So I did all that work just to get things in that order. And that's just the right-hand side of my Laplace transform. So the right-hand side, I take the Laplace transform of f of t. And because of that shifting theorem, that will be e to the minus as, so in this case 1s, so e to the minus s times the Laplace transform of this g, which I'm going to write as t each time, because remember g equals t, so I'm just going to sort of simplify it there and put t. And then minus 2, and then e to the minus as, so minus 2s, and then times the Laplace transform of t, and then plus e to the minus as, so e to the minus 3s times the Laplace transform of t. So I'll do that for each one. And if I look at my chart, the Laplace transform of t is equal to 1 factorial over s to the 1 plus 1. So this would be 1 over s squared. And so each term has one of those. So I would have on my right-hand side my Laplace transform of f of t would equal 1 over s squared, and then multiplied by e to the minus s minus 2 times e to the minus 2s plus e to the minus 3s. So those would be my Laplace transform of the right-hand side. And then the left-hand side, would be the Laplace transform of y first derivative plus y. So that would equal capital S times big Y of S minus y sub 0. That would take care of the y first derivative. And then plus the y, so that would be big Y of S. So S to the 0 times big Y of S. And this equals S times y of S plus y of S minus, and then what was y sub 0? Y sub 0 was 2. So minus 2. So if I factor out the capital Y of S, I'm left with S plus 1 minus 2. Okay, now I've got the right-hand side and the left-hand side. And let's put those equal to each other. So y of S times S plus 1 minus 2 equals, that's the left-hand side, equals the right-hand side, which is 1 over S squared times e to the minus S minus 2 times e to the minus 2s plus e to the minus 3s, like that. Then I divide, or add both sides. I add 2 to both sides, then divide by S plus 1 to solve for y of S. So y of S equals 2 divided by S plus 1 plus 1 over S squared times S plus 1, and then multiplied by e to the minus S minus 2 e to minus 2s plus e to the minus 3s. There we go. So then I think we have to figure out what this 1 over S squared plus, or times S plus 1 is. We've got to deal with this. So I think partial fraction decomposition is going to be the way to go. So let's see. 1 over S squared times S plus 1. And then that's going to be equal to A over S plus B over S squared plus a C over S plus 1. That would be my decomp, or my algorithm to find A, B, and C. So then 1 equals A times S times S plus 1, multiplying both sides by S squared times S plus 1. And B would be, so plus B times S plus 1 plus C times S squared. And let's see, if S equals 0, that's the obvious one, then I would have B equals 1. And if S equal minus 1, that's another pretty obvious one, then C would be equal to 1. Okay, so now I gotta still figure out A. So let me write this. I'd have 1 equals A times S plus 1 plus B, which is now 1. So S plus 1 plus C, which is 1, so plus S squared. And I got to solve for A. So this would be S equals, let's do 1. So that I'd end up with 1 equals 2A plus 2 plus 1. So that means A equals minus 1. Wow. Okay. So Then, see if we can get this to come to a finale here. Y of s equals 2 over s plus 1. That's just from the first term. Then I do my partial fractions. So I do plus 1 over s squared. That was b. And then minus 1 over s. That was a. And then plus 1 over s plus 1. That's the decomposition. This part. And then that needs to be multiplied by e to the minus s minus 2 times e to the minus 2s plus e to the minus 3s, like that. Whew, yikes, right? And then I'm going to take the Laplace transform, the inverse Laplace transform to both sides of that. So here we go. If I take the inverse of y of s, well, that's going to be y of t, by the way. The first term is right on our chart. So that's 2 times 1 over s minus 1. So that would be our first term, right from our chart, is just 2 times e to the minus t. And I forget what number that is on the chart. Let me look. That's number 3, and you just pull out the 2 in front. And then for the rest, you've got the shifting theorem business. So let me see. I'm gonna run out of room when I write this, but so for this one, the a is equal to 1. So I have u sub 1 of t, and then that's going to be multiplied by, so remember 1 over s squared is t, but I need the minus 1, so this will be t minus 1, then minus, and so this is t, but I have to shift, so I need the t minus 1. Then this is just 1, so there's nowhere to put the t in, so it's just minus 1. And then the last one will be, this is, from that same number 3, would be 1 over s, 1 over s minus 1. So that is e to the minus, and then it would be t, but we need t with a shift, so t minus 1. So that takes care of that. And then the next one I'm going to write down below would be minus 2. So minus 2. And then we have the u 2 of t. And again, we're getting that from this e to the minus at. And then it'll be the same as above, but we have to shift by 2. So this will be t minus 2 minus 1 plus, this was missing a plus, that needs a plus, plus e to the minus t minus 2. And the same for the next one, so plus u sub 3 of t times, and then t minus 3 minus 1 plus e to the minus t minus 3. Okay, and if I sort of wrote those down the column, which is kind of a weird way to write it, but I would have ran out of room. So I think we can simplify some of this. So y of t equals 2e to the minus t plus, let's see, we've got minus 1 and minus 1 for minus 2, and we've got a t. So we should write this as u sub 1 of t times e to the minus t minus 1. I suppose we could distribute that negative in the top, but I'm not going to for like emphasis. And then plus t minus 2. So I just simplified this a little bit. And the same idea for the rest of it. So minus 2u2 of t. And this would be e to the minus 2 t minus 2 minus t minus 2 plus t minus 3. I'm still going to run out of room, so I need the plus u3 of t. I need to put that down here. So e to the minus t minus 3, and then you're going to have minus 3 and minus 1 is minus 4, so plus t minus 4. Okay, I think that's the right answer. All seems to check out to me. So you can tell that these are get really sort of nasty pretty fast.